First thing we're going to look at is this top group. These rare earths are characterized by the low boiling points. We've reduced them from lanthanum oxide. They're easily purified through sublimation. That is, we heat them up and it goes from a gas to a solid, or I'm sorry, a solid to a gas. And that gas then collects on a collection plate. These don't react with tantalum very much, so it's easy to keep them pure with respect to tantalum. However, when we're done making it, it's more like I would call the consistency of spaghetti squash, because we can't arc cast these into nice ingots. Their vapor pressure is so high. Thulium, for example, has a vapor pressure of 74 millimeters at its boiling point, or melting point, I'm sorry. To give you a reference, atmospheric pressure is 760 millimeters. So it's almost a tenth of an atmosphere. So if we tried to arc cast it, we'd lose 50% of the metal. It would boil off. Process. We have to prepare all our tantalum crucibles in advance. We have to dry the oxide to desorb any water, carbon dioxide. Then we have to make lanthanum chips for reduction, and we actually mix those together in a bag, kind of like you're making a shake and bake, and we'll stuff those into a crucible, our tantalum crucible, put it in an induction furnace, and we'll heat it all under vacuum, and that's where the reaction takes place of the lanthanum oxide, or lanthanum becoming lanthanum oxide, and the metal, for example, samarium being released. Then we'll do another step where we sublime it. And then we simply strip the tantalum off like you're opening a sardine can off the tantalum. Europium, we go to the next step, is we actually extrude the europium into rods. And the reason we do that is to reduce the surface area of the material because it's so reactive with air. This finely detailed image, which is kind of hard to see from where you're at, and the fine lines in this bad projector, shows our setup. This is a quartz containment for our vacuum. This hatching is graphite insulation on a tantalum boiler or heater can, as we call it. This is what we call the boiler can, or reduction vessel, also made of tantalum, and here's the mixture. Heat it up, the metal gas comes up through the baffle and collects somewhere on the inside of this condenser can. This is the image of the induction system. These are the coils. This is the quartz containment. This picture here actually shows you what it looks like when we've made the sublimed material. This is ytterbium, and if you remember the condenser can sticking up in the top of that schematic, this would be the top of the condenser can, and it would have come down a ways, and then the boiler can would be somewhere down here on the floor. All the metal moves up and plates itself, and you can see this kind of stringy texture to the metal. Next group, the light rare lanthanum, cerium, neodymium, and praseodymium, are the next easiest to make. If you remember from the vapor pressures, they had the lowest vapor pressure, i.e. highest boiling points, and they were very low melters. We can use that to our advantage because we can vacuum cast these without loss, meaning any impurity that's volatile, we melt it under vacuum and they come out, leaving the metal we want behind. And the tantalum solubility is pretty low, but because the vapor pressure is so low, we don't distill or sublime. We do what we call is pouring. And if you go to the Ames Lab YouTube channel, you can see a video of the pouring process. We'll look at it schematically. We call it lanthanum decanting on the video. Decanting really describes what we're doing more than pour. Pour is our local slang for what we do. But the process is very similar. We dry the oxide, but we do one more step that we don't do in the first group is we fluorinate the oxide. Mix that with calcium, heat it, remove the slag. We'll do 3 reductions, one on top of the other. We'll see that. Then we vacuum cast at high temperature. And this pouring process is where we cool to just above the melting temperature, or I'm sorry, precipitation process, and we precipitate out the tantalum that may be in there. Then we decant or pour away from the precipitated tantalum. In this case, we can machine off the crucibles and we can cast into arc melt ingots. Our fluorination starts in a fluorination furnace, which is really pretty boring. It's just a box with a tube through the center of it. Even the schematic is kind of not very thrilling, is it? We feed in HF gas and argon. Comes over here, get a gas-solid reaction, produces The rare earth fluoride, water is a byproduct, and we push that all out the end in terms of a gas. We take that high purity fluoride and we do the reduction. Well, this, if we imagine that these purple lines are layers of neodymium fluoride and the yellow lines are layers of calcium metal, this is how we'd pack the reduction. It's almost like packing sand in some cases, and you're doing this in a 10-inch tall crucible. So it's not very fun for our technicians to do it, but they do a good job of it. We'll heat that up, they'll react, and what happens is they'll separate. The rare earth metal of interest collects at the bottom, and the calcium fluoride slag floats on the top. You've got to be hot enough to melt both of these, but they separate like this. Hopefully you'll take that calcium out by just turning it over and it drops out, if you're lucky. Then you do it again, right on top of the previous metal production run there. And you do it again. So we do that about 3 times. We end up with several kilograms of metal. We'll move on to the vacuum casting step, which is essentially exactly as it sounds, melted into a vacuum. Here's the reduction process and or vacuum casting process in action. It looks exactly the same. And when you're done with the reduction, here's our calcium fluoride slag. This one did come out very nicely. If it doesn't come out nicely, you literally have to get a foot-long chisel and chisel it out by hand, and it takes you a long time. And you can't be very aggressive with the chiseling because you don't want to damage your crucible while you're doing it. When we've done the vacuum casting, then we'll do the pouring. And this is a schematic version of our pouring process. Here is the original reduction crucible, and then we did the vacuum casting, and we drill holes in the bottom of it. And then we heat this up very fast, and it pours through the bottom of those holes, and what it leaves behind is the tantalum precipitation. And we lose a little of our metal, but not a lot. This is a picture of the pouring process in action. This first one is before it's melted, and you can see, kind of see the texture on the surface. This more mirror-like surface indicates that it's molten, and it's partially flowed out because here is the initial level of the metal.